All right, so
Oh, I wanted to ask, are you still planning on, didn't you say you were going to post a homework problem over the weekend?
well, I was going to post a video. The homework problem I think I gave to you.
Right, you gave it to us,
Yeah,
but you said you were going to post a video
I didn't, and
talking.
what that's what I was just saying. I'm actually going to go over that information with you today.
Okay, I apologize.
That's okay. I didn't have time to do it, quite frankly, and I thought, you know what? I think it's kind of easier in a live format anyway. That way, if you guys have some questions, I can just answer them. Okay.
Okay, sounds good. Yeah,
So
my
we'll,
my boss was calling just a second ago.
okay, no problem. Well, we'll piggyback that onto this lecture. Okay. This will be a second section. All right,
Sounds good.
so let's go ahead. We'll get started. So this is talking about basically route finding. Your chapter is getting there quicker with geospatial technology, and it's going to talk about several different things. So one thing we're going to talk about is what we call networks. So networks use some terminology that's kind of exclusive to them in the GIS world. Um, we're basically network is basically a roadway system, or it could be a stream system or anything like that that has links in it, but they use some different terms in that when we get into GIS. And then we're talking about address matching. So this is a big deal because this is actually how, when you type in an address, how it actually finds it, and it's kind of interesting to see how it does it because it's really not exactly giving you the answer. It's just kind of a close approximation of what the answer would be. So we'll kind of look at that. And then we're going to look at what's called shortest path concepts, how not so much the nuts and bolts of how it does it, but just some of the concepts that they use for shortest paths. And then we'll look at how networks can be used in geospatial technology, which you guys, I'm sure, are all very familiar with already. So that's going to be nothing new to you. And I think then that's it. So let's get started talking. And one of the things, the chapter that the author begins to talk about, if most of you guys have used some kind of vehicle navigation device, but if you have used one of these, let's see if I missing something. Yeah, okay. If you have used that, basically it's a device that's going to plot your position on a map, and it uses kind of two things actually. It's not just one. It's using GPS technology to obtain your location, but then it has to plot that GPS location on a base map. So you have to have both things in place. So I mean, at one time it was considered very revolutionary. I'm not so sure that you would consider it revolutionary today because pretty much everybody uses it. But it's used to certainly find precise current location. It's not always going to be perfectly precise though, so we'll see why that is. And it can plot that on a map for you. And then you can do things like determine proximity to things, such as nearest services, gas stations, fast food restaurants, or other things that amenities that you might be looking at. And then you can also use it to determine quickest route, perhaps, due to, like, say, traffic patterns. So if you have a real-time feed into this, it can tell you, that you've got a traffic jam somewhere, and it can actually reroute you, which a lot of these now have real-time feeds. Or you can have crowdsourcing stuff where people key in things, and actually then that's a real-time feed to it. So this is an example of a particular kind. And of course, you have them on your phone essentially, and you can also have them built into your cars. So a lot of times when you buy a car now, it already has this information. But it's all, the key thing that's important to understand is really two technologies in one. One is this map itself, which is your base map. So that's your GIS component, and it has the attributes and it has the vector files. And then GPS is providing your current location. And basically it's bringing those two together and mapping that location. Okay. So these devices rely on GIS style systems. So basically it really is GIS in that sense, but it's just focused to one thing. So you're not going to be able to do analysis with it like you would with a full-blown GIS. But particularly in your handheld data, you have to have that spatial data in some kind of form. And usually we're looking at a roadway or a road network of maps. So this is where a lot of the information comes from or can be corrupted. So if you have a bad road network map, obviously you're going to have issues, or one that's outdated. But the utilization of that road network map allows you to determine those things. And like we said, one of them is going to be what we would call shortest path. So there's a lot of things that could determine that, as we'll talk about that here in a little bit, what we mean by shortest path, because that doesn't necessarily mean the shortest distance. That could be based on time or energy or all different things. Then the other thing is you can match an address to a spatial location. And I'm certain you guys have had problems with this, but if your address information isn't correct, it doesn't exactly put you where you're supposed to be. And I remember early on having an issue like this where we was trying to find a hotel that we had reservations at in a remote area of Southern Illinois, and it was the wrong address, I think, attribute. It was sending us north and it should have been west or vice versa. It took a while to find the place actually, because it kept taking us the wrong direction. So again, the base map and the address information has to be correct. So this same technology can be employed for other things. The 911 call systems are one thing that are definitely using this, and so is things like Google Maps and MapQuest and those kind of services. So we know that real world items can be handled in GIS, and a particular feature that we talk about for GIS is what's called a network. Okay, so we've looked at things like polygons and line features and point features and those kind of things, but now we're looking at one particular type of thing, which we define as a network. So a network is basically just any kind of series of lines and junctions that connect together for modeling concepts, okay? So the junctions, another name for a junction would be a node or a switch or a valve, and an edge is the same thing as a line or an arc, okay? But anything that we can connect together in a series of things like that, then we can think of that as a network. So for instance, a street or highway network, that's your classic example. Stream networks, which a lot of people might not think about, but if you're doing hydrology types of studies, you have the head end of a stream, and then that goes into another stream, and then those streams feed in, and then ultimately you get into rivers like the Ohio River, and those are just all big networks of interconnected waterways. So those can be modeled as a network as well. And the mouth of each creek, stream, river, whatever, would be your junction at that point, and your edges would actually be the flow of the water itself. And things like power lines, those could be modeled as networks, or any kind of linear utility, water lines, power lines, gas lines, all of that kind of stuff. So the GIS is using several what they call basic features. So different GISs use different terminologies. And ESRI, I think they use the term junctions and edges, okay? But we could think in terms of node and line, or like I said, it could be, you could think of a switch or a valve, okay? So those are just kind of examples. So a junctions, it's just a place, a term where you're using a node, it's a place where edges come together in a network. It also allows things to transfer from one point to another, such as an interchange. So if you have, let's say, an interstate highway and your exit, got an exit ramp and an entrance ramp at that point to another highway, that could be modeled as a junction, which allows you to enter and exit, but it can also limit what's going on. So you guys can all think of examples where you can exit the highway, but you can't get back on perhaps. So that junction would have that function of being allowed flow one direction, but not another. Or where you have a two-way street that goes into a one-way street or vice versa. So those are the things where junctions would be very important, okay? So these are gonna act like valves or switches, okay? Now, typically it could also be a starting point, an intersection, and an ending point, such as a cul-de-sac perhaps. But then anything that intersects in between would also be considered or produced as a junction. Also, and we'll talk about this maybe later, but junctions are going to have attributes associated with switching activities, okay, like stoplights and stop signs, and like I said, allowing you to go one direction and not another. So those would be the function of that junction or the node. Well, then the other thing we have is the edge, and this is the term used for the linkages in your network. So again, it could be a line, you could think of it as an arc, and it's just flowing from one to the other, okay? So links, we can call them lines, we can call them arcs, okay? So basically, you can think of a city's road network consisting of edges, which are your roads, interstates, subways, and junctions, which would be things like entrance ramps, exit ramps, cul-de-sacs, or any other intersection, but they are allowing things to happen. Now, let's think about this too. You can think of also lots of interstates, they're considered limited access. So you don't have an interchange everywhere. So where you have, let's say, a state highway that is crossing an interstate and it doesn't have an intersection, even though visually on your map you would have these two edges cross, there would be no junction in place there. Okay, so those are very, very important concepts. Okay, so the other thing we need to deal with when we talk about a network is what we call connectivity within that network model. So this is the way that things flow together. So from the edge to the junctions, and the junctions, remember, there are the switches. So to define this properly, you have to have proper connection between objects. So intersections allow flow from link to link, or they may not allow flow in one direction, okay? But overpasses that don't connect to roads are not going to have any connectivity. And so that's an important thing. I think your author, if you read the book, he talks about there's cases where some of your networks are wrong sometimes. So there was a case where a guy was following his GPS navigation system, and essentially it told him to turn off of the highway basically into a cliff because they had a junction there that really didn't exist in the real world. So that kind of stuff actually does happen sometimes. So this is a good example. This is what you would call a tiger file. This happens to be Virginia Beach. And what we've got going on here is there is a boulevard here that's highlighted in blue, so that's been selected. That's, if you read the section in the book, that's Virginia Beach Boulevard. But that represents a network just for that. And it's composed of a bunch of little line segments that go together. So you might think of the whole blue line as one polyline, and basically it's going to have a lot of little vertexes. But the way the GIS handles it is each little line segment is going to have its own record in the database for this road. So you might have, there might be 200 or 300 links that create this, and each of those links is going to be a record within the database, and then it's going to have attributes associated with each of those. So it could be things like street names and addresses and, you know, all kinds of stuff, as we'll talk about here in a minute. So if you think about that, visualize this, each one of these little road guys in here could have their own records within a database. So you can see just for this street network in this city, Virginia Beach, that's pretty involved right there, especially when you start adding the attributes and the number of records that can be happening there. So just understand, just because this is Virginia Beach Boulevard doesn't mean it is one record in the database. It's broken up into literally hundreds of little links with junctions at some of those link connections and not at others. All right. The other thing to think about too, and this is really important, is that this picture was produced, who knows, let's say maybe in 2005. Now we know, because we're involved in the building activities, especially things like subdivisions, that's constantly changing out there. Roads are constantly being added, subdivisions are being, you know, roadway networks are being added. So this might be way outdated, and so information can only be utilized what's in this database. So we have to constantly update these base maps to be able to have a valid picture. Okay, so there are lots of different geospatial network files that are available, and a lot of these are federal government based, and a lot of them are free. And in fact, what we were looking at, this is what's called a tiger file, and this comes from the Census Bureau, and Census Bureau has been developing these things, goes back, I think, to the 80s. And all of this stuff is free. And it used to be with these guys that they were better files in the urban areas, but they were less valid or less accurate when you got into the rural areas. But I think they've changed that quite a bit, so that's all changed. All right, so we have what's called a street center line, and this is a file that just basically contains your line segments representing your roads, and it would also have your junction information. Okay, so it'll contain different types of roads depending on who created it. So you might have the arterials and the collectors, and then you have maybe even more local sets. So again, if you're just looking at different levels, you can get different amounts of information.
Question.
So yes, go ahead.
So just do the junctions and the edges each have separate records, or is it the junction part of the edge record?
I believe the junctions are actually, if they're a node specifically, they're probably modeled as a point.
So then they do have their own
They would
separate
have to be their
records.
own separate section. Yeah, right. So that would probably be the way it's handled. Yeah, pretty sure. And we'll look at some. Actually, I don't know if you guys have files that you can actually look at, but the USA stuff that I gave you, I think there are some roadway networks on there. I might be wrong on that. So you could look on that, but I think if you're going to see, it's probably, if you look at the line file, all you're going to get is line information. Okay, does that make sense though, that it would be represented separately? Because they really are different, right? But they have to be connected together, right? So, okay, that's a good question. Good question. So the one that's produced, like I said, has been produced for a while now, is what's called the Tiger line file. And this was produced by the US Census Bureau. And originally they had what were called DIME files. That was also an acronym. I forget exactly what the acronym was. So the DIME files, I think, came before the Tiger files, and Tiger line files have now kind of superseded that. But this contains line segments that correspond with the roads across the whole US. And that Tiger stands for Topologically Integrated Geographic Encoding and Referencing. So that's where you get the TIGER. So it basically just represents a segment of a road network, and each segment's going to have multiple attributes assigned to it. So those attributes are dealing with lines. So kind of that's your answer right there, Ben. It has to be only associated with a line, because there's no information on a roadway that has anything to do with connectivity, okay? It might have velocity, it may have, you can have two-way or one-way traffic, but it's not going to tell you it can switch from one to the other. So you do have to have that integrated someplace else, okay?
Okay.
But you can have a lot of information associated with each of those. But the cool thing with these files is they're fairly accurate. They've been around for a long time, and as a product, you can go out and download this thing for free. So you guys could go right now to Tiger files. You could go to the Census Bureau and download, the whole Cincinnati or Hamilton County area, and then you could put that in your GIS and be utilizing it. And besides the line network files, you're going to get the attributes associated with it. You can also tell it what level of information you want to. In fact, if you go to the book, he talks about these a little bit on one of the hands-on applications. You might want to check that out, because that's actually pretty cool to visualize and look at. So this is an example of this same file we're looking at. We brought this in. This was brought into ArcMap, you can see, and you notice that is a line type object. And you can see some of the attributes associated with it. So there's things like, it's kind of hard to read some of that, but that F node, that's the from node and the to node. So that's where it starts, that's where it's in. So that's kind of like your zero station and your higher station. The length. So each one of these is just a little separate line segment associated with that blue line that's highlighted there. So each one of these little guys has a record. And then you got names, you got all kinds of stuff. And you can see this bar scrolls over. So there's all kinds of attributes associated with that, which there could even be more than what they had. They might have clipped that out when they did a query on that and did a subset of just the information they were looking at. So the Tiger line files is going to contain several what are called standard attributes. Now I think over time this has changed a little bit, so this might be a little dated. I think this was the original. I think I've got a picture here that's going to show you a little bit of a difference. But some of the standard attributes would be like what they call FEDIRP. That's a prefix direction of a road, such as the letter N for north or south. The FE name is the name of the road, such as broad. FE type is avenue, and then you have this suffix if it has it, east. So these are some of the basic ones, but remember there's going to be a lot of other information that can be associated with this. You could have census feature class, because these are census files. That's pretty important. And then it's got address ranging across it. So This was be your from address left and your from address right. So this goes from the from node to the to node. And notice what this is saying. For instance, you might have from 101 to 199, okay, on the left side, and from 100 to 198 on the right side. So what we're seeing is even and odd numbers on the left and right side. Here's your to address. To address left, to address right. So basically, if we go back, let me go back to this one. This is telling you the range it's starting at. So it starts at 101, and it starts at 100 left and right. And then the ending point of that node is that point and that point. So between any segment is going to have a from node and a to node. And then when you hit the next segment, it's going to have a from node and a to node. So it just goes on. So there's a ton of information. And this addressing information is going to be important when we talk about address matching here in a minute. So that's why that's so key to the whole process. And then you've got zip codes left and right. They just got a whole ton of information. Now, I think what we were looking at were Tiger files earlier on, but the Tiger files have changed a lot of that. So actually they've showing in this is kind of nice. This is showing you what Tiger files look like in the year 2000. Then they updated and changed all that. So when they went to 2014, they changed the attributes. And then the national map, which is produced by the USGS, we talked about that. They use a little bit different format. All of these, you can get Tiger files in all of these forms, and you can also get national map information from the USGS. And so you can use these different base maps depending on what you got. But these are then, just understand, these are attribute headings. And notice how it's changed over time. So what we were just looking at was the from address left is now the left from address. So that's good. It's just weird. These have changed. And notice what they call it for the national map. They call it the low address left. So basically, these are all talking about the same piece of information. I just got used to this because this made sense to me, from address left. But I think that's left from the high number is kind of what that's saying. So it's very interesting how this works. But you would almost, if you're dealing with this in any GIS sense, you're going to have to know what these attributes are, because when you get into that table, all it's going to show you is just those headings. Let's go back and look at that real quick. What I mean, you can notice this is all you're seeing. There's your heading, there's your heading, there's your heading. So you have to have some kind of description to know what that means. And you can, when you download Tiger files, you can also get information that this defines this. I think there's a PDF file or something that you can get for this. So if you don't know what this is, you won't know that that's the prefix or the suffix or the address left or right. Okay. Okay, so your attributes, they define the characteristics of your road segment. So you would have similar attributes found in a typical road network data. Any incorrect attribute is going to give you problems in your searches and those kind of things. So that doesn't necessarily mean that you got an incorrect base map in terms of the actual picture. So the vectors might be fine where they're located, but if you have incorrect attributes associated with them or matched with that, that's going to give you problems. And like for instance, I was just talking about where I had an issue trying to find a hotel once. It was because they had a north where it should have been a west, and those were swapped. So it wasn't a case where the GIS was taking me, or GPS was taking me in the wrong spot, and GIS was matching up, but what we were typing in basically wasn't matching with what they had on there. So that was kind of the thing. So your navigation system is going to give you an incorrect value based on, whether it's east, maybe actually west. And that kind of stuff happens. It eventually gets winnowed out. I'm sure over time that gets corrected, but as we build this stuff more readily, it's just like anything else. When you're dealing with huge amounts of data, you're going to have problems in it. Okay, so Tiger files typically can be used for a base map for a lot of applications. So if you're building a GIS just locally for yourself, or maybe let's say you were a rural county that didn't have access to having your whole county flown or something like that, and you wanted to begin building a base map, Tiger files are a good place to start, because you could just import these in for that particular county, and you would basically have your roadway network. It wouldn't be perfect, but it sure would give you a start, and it would also have a lot of the attributes already associated. And then it would allow you to do things like pinpoint particular addresses along a stretch. Okay, so let's talk about address matching. So address matching is the process of where you are trying to find a location out in the real world, and it's basically pinpointing that on a map that you can visualize. So a service such as MapQuest or similar software, you can type in a query and it's going to give you a location. So for instance, if we typed in 1600 Pennsylvania Avenue, Washington, D.C., that's going to be enough to typically in most databases get us where we need to go, which happens to be the White House. So what happens here is the software has to translate those characters into a map location. So it's a bit of a process depending on how that does. And then once you type that in and translate those characters, then it'll try to match things up, and then it then tries to match that location with your GPS location. So this process, when you type something in and it finds that location on your map or your GIS, is a process of what we call address matching, or it's also referred to as geocoding. So those terms are synonymously used. And I think some softwares use address. I think ArcGIS, well, they use both, I believe, but they call it a geocoding process, but you're also doing what's called address matching. So example, here's a map that you have, and you've typed in that address, and you can see what it did is it pinpointed that location for you. Okay, but let's kind of look at how does this do this? How does this happen? Okay, so address matching is the process of using text that you type in to actually pinpoint that address on the location of the map. So it just doesn't automatically know that when you type in 1600 Pennsylvania Avenue, oh yeah, that is the White House. Okay, it doesn't know that. All it has is it has a roadway network file with all this address information we just looked at, and it has what you typed in, and it has to make it match. So it's not a real simple process. So what it has to do, and of course that geocoding we said is the same thing, what it has to do is it requires several steps to get this to match up, okay? So the first step, you have to have that reference database in place. And again, as we just talked about, as precise as your database is going to give you that good match, okay? The better that is, the better your match is going to be. Now, here's the other thing to think about. Address matching is not perfect, and it kind of does it on a hierarchy. So it'll say, okay, I think the best location for what you typed in is here, but it could be here, 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 or here. So you might get several different locations based on that, but it could nail it right on the nose if everything matches perfectly. So the reference database is going to be used as your source for geocoding. Okay, so that's the first step. You have to have that in place. And that will include your road network files, which has your geometry, but it also has all the address information associated with it via those attributes on the attribute tables. Okay, the line segments have to be linked to those attributes also. So any good reference database, this stuff's already done. So if we downloaded those Tiger files, that would already be a done deal. Okay, so the next thing, then, we have to type in that address, and that address has to be what's called parsed, and then standardizing using address standardization techniques. So parsing is the process of breaking down the address that you type into little chunks. Okay, so when you parse something, you're breaking it down into little chunks, and then you're matching that up in standardization technique. So parsing, you break it up into component parts, and then you standardize it by breaking those or setting those component parts into a regular format. And then it's going to do the match. So here's an example. So if you type in, you're typing in 1600 Pennsylvania Avenue Northwest. So what it does is it isolates this for 1600 and then says this is a number. So that's under the number, that's standardized it to number. The word Pennsylvania is the street name, so it parses that out and places that in this section. It recognizes that there is no prefix, so notice there's nothing here. Avenue gets standardized into AVE. So in other words, there's going to be probably what's called a lookup table or another database that holds that information. And so it recognizes if you type in AV or AVE or Avenue, it parses it into this and breaks it into a standardized format, this. And then you have the suffix of Northwest. So here's your parsing process. You've broken it down into these pieces, and then you've standardized it. And then it will go into that database, and it will search records until it finds something that matches this 100%, or maybe 80%, or 50%. And if you're spelled Pennsylvania wrong, you might not be in the right spot. If you don't have the suffix Northwest, obviously, you're going to have issues. But you can kind of see how it's taken different ones and broken them out. So notice if we go down here to this Holocaust Memorial Museum, it's 100 Raoul Wallenberg Place, Southwest. You can see how that broke that out. So that's the parsing process. And again, a lot of it would have to do with the user typing it in. And just a little character in the wrong spot. If I typed in 160 Pennsylvania Avenue as opposed to 1600 Pennsylvania Avenue, it could find another match somewhere completely different. Right? But it's not perfect, okay? So one of the things is once it's parsed it and standardized it, then it tries to take that, it takes the matching. So the GIS will find a line segment that references that database and correlates as closely as it can to what it's standardized. And it's not, again, it's not always going to be a perfect process. Best match of that component will produce pull out the line segment, and it will then typically match it up and give you some kind of symbol or say, yeah, this is essentially where you are. You may get a ranking scheme. So it may find, well, like I said, this matches 95%, but you have a couple other ones that maybe ones that matches 90 and one that matches 80. So at that point, the user may be directed to, okay, here's several locations. And it's up to you to kind of pick out which is which. Okay, so it may plot a point at the location along the line segment. It may plot several points if it's really ranked it out. So these points then, when they're plotted at an approximate location along the selected line. And so here's another thing to understand. And we're going to take a look at a little example here why this is. These points are not going to be perfect because there is not an exact location for every address along that line, okay? So the points aren't going to be perfect because you don't have an exact location along the line. You just have a generalized location along that line. And it uses a process called linear interpolation to geocode an address. In other words, to find its location. So when it plots that point, it may not be exactly where you think it is, okay? So the location is going to be approximate due to the interpolation process and also due to the database itself. And it's not going to necessarily match the exact location of that address. Okay. For instance, the reason this can happen is the streets that contain only a few buildings are going to have potentially large plotting errors. And I'll show you a picture of that here in a minute. Okay. So this is kind of showing you this. I'm going to go through this mathematically, but I want to show you what's happening here. We're looking at this line segment right here. And this is what's called Wick Avenue. This is just a small location of it. So you have an address range. It starts at 300. That's your from node, and it goes to 398. And then this is the right side. This is 301 to 399. So you typed in this address, and it pinpointed that location there. Okay. So basically, it's just linearly interpolating that location, but it may or may not be right. Okay, so let's take a look at something here real quick. I'll show you an example of this and why this doesn't necessarily always work. Let me pull this guy up. So let's take a look at, let's do a quick example. Let's say you're in a rural area. So here's a roadway, and it's got a cross street here and another cross street here. So we have a node right here, and we have a node right here. So one of the attributes for this is the length. We'll call that length is 5 miles, okay? So that would be from, let's say, node A to node B. And let's say that we are looking at the left side. And so let's say the left side is going from 800, address 800 to address 2001, okay? So on this rural stretch of road, okay, you may only have a couple of houses, maybe one here, maybe one here, and maybe one here. And the address of this thing might be at 1000. So that doesn't necessarily mean it's proportioned perfectly in here, because especially on rural roads where you don't have a lot of properties, this doesn't necessarily proportion perfectly. So what could happen here is when we do a linear interpolation, what we're looking at is for the distance. Let's say we want to know what the distance is from A to that point right there, okay? So we're going to call that distance X. So we're going to say that X is to the address range. That would be 1,000 minus 800 as 5 miles. 5 miles is to the address range of 800. Well, I'm going to do that the other way so I don't get a negative. 2001 minus 800. So we could solve this proportion. So X is going to be 5 miles times 1,000 minus 800 divided by 2001, 800. And when we solve that proportion, let's see what we come up with real quick. I think it's about 0.83 miles. So I'm coming up with an answer of about 0.83 miles. So basically then the system would come down that distance and put it, and you might actually get the spot here as opposed to where the house is, okay? Because where it actually is, the actual distance, and what the linear interpolation is giving you could be two different things. Does everybody kind of get the idea? Particularly in rural areas, that's going to be more of an issue. In an area where you have lots of houses, parcels that are maybe, let's say, maybe 100 feet, you're going to get a pretty true location. But because this kind of thing can happen in rural areas, you can get that much can be a couple of 100 feet off from where the actual true relationship is. So the thing to understand is that one thing that's going on here, we're not actually getting, we don't actually know exactly where that is, okay? It's done through a linear interpolation process. So even like if you think about like a 911 call, if they're doing that and it's using a linear interpolation, it's not necessarily taking you right to that location. It might be off a little bit. So a process of doing multiple address matches at one time is a process called batch geocoding. And this is a pretty involved thing. I've played with this a little bit in ArcGIS, and it's a big deal. Basically, you're matching, like, say, a whole string of data. So if you were looking for, like, plotting all of the, let's say, Arby's restaurants in the city of Cincinnati, batch map, you know, you're trying to batch those. This would be called batch geocoding. And this is, it's really a difficult kind of thing, and it takes a long time to do. But once you set it all up, it'll try to match, you know, in a hierarchy with what it says is the best. But if no match is found or the ranking is poor, it probably won't display anything. And then it might flag those ones that it can't find. And then it basically has you as a user have to go through and figure out, like, maybe something's keyed in wrong, or, you know, maybe a street's not really there, but that's not on the database, but actually does exist, those kind of things. So a lot of GIS people, particularly that might be doing marketing, those kind of things, they do a lot of this batch geocoding kind of process, where most of us users, we're just searching for one thing. You know, we want to get to a coffee shop from where we are. You know, we're doing a single geocode. That's pretty simple and pretty basic. Okay. So once your address has been matched, a coordinate location can be calculated, and that, of course, can be matched to your position with GIS. So it gives you maybe an XY value, maybe a northing and easting, or a latitude and departure, those kind of UTM, northing and easting, or possibly a lat long, one of those kind of types of things. And once you have that information, then you can match that to your location in GPS. Okay. So that gives you that spatial reference, and then that can be used for other purposes as well. Okay. So here's an example of typing this in, doing a search. You know, you entered the address location, it was parsed, it was matched. It broke it down and it found the location of where that is, and then it shows it on the map. And this location is probably pretty decent because notice this is pretty dense right here. All of these buildings, footprints that you see on those might actually be parcels, but all those parcels or building footprints, they're pretty dense. So the location of what you're typing in there is probably going to be pretty true. But as we said, when we get into the rural areas, that's going to be off quite a bit more. Okay. So again, we talked about this. You're going to get, it's a powerful process, but a lot of errors can occur. Okay. Parsing errors can occur due to data input. So this would be probably the user inputting that number. So like I said, if we typed in 160 versus 1600 Pennsylvania Avenue, or we spelled Pennsylvania wrong, or those kind of things, that would give you a parcel error. Okay. Because of the fact that we type certain values in differently, it's going to give us a lower ranking, and it may be plotted elsewhere on the database if it found the match. If you're doing batch processing, you could have mistakes within the addresses and the stuff that you have in the database that you're trying to match. So that's always a possibility as well. You could possibly have line segment errors. I mean, that's a possibility. Remember, these things aren't perfect. So even the stuff that you get from the Census Bureau, it's not perfect. And like I said, in the original days of Tiger files, it was always considered pretty decent in the urbanized areas, but in the rural areas, it was definitely considered really not a perfect world, but that's changed quite a bit. So you could have incorrect attributes associated with a line segment. Streets are not part of the reference database, like we said. You know, if we've got an older database and subdivisions have not been created in that database, there's no information out there. So that wouldn't be a parsing error. That would be an error just due to the fact that its line segments don't exist. Okay. So there's been other methodologies that have been used. Now, the linear interpolation is kind of cool because you don't have to hold every address within that line segment. You just hold the start and the from and the to nodes information, and then it can actually just calculate it on the fly. But there's some newer methods that allow you to do it a little bit differently. One is to use a point database instead of a line and doing in linear interpolation. So what this is saying is you're actually creating points that are essentially along a line at the location of where every address exists. Well, you can think about that being a nightmare because that would require literally millions of points to portray the same thing that a line could show you with just doing linear interpolation. But technically the point would be better because the location could be a real precise point. So to do this would be a big job. You can also, and I think I've read a lot about this where you're using the point location at the centroid of a parcel of land. Everybody know what a centroid is? What we're talking about by centroid?
Yes.
Okay, so it's the geometric balance point of that. So if you have a polygon, it finds the centroid, which is a common application you can do in any GIS. So you can have you've got your polygon parcel. Attached to that would be the address of that thing, and it can just go out and find the centroid based on what you typed in. This one actually, I think more people are starting to use this. It's a little bit probably more precise than linear interpolation, and it would just be a matter of having the address attached to the centroid location. That's not a big deal. So it's just you're matching it based on that point representation within the parcel. So it can find it, and it places it immediately adjacent to the parcel on the line segment. So once you've got those multiple locations geocoded in a GIS, then you can do other things with it. So one is to talk about route finding. So you can examine routes between locations. So if I've gone out and I've found, like, let's say a coffee shop, and then I found a shoe store, and I found some other kind of place. Once I have that information, then I can have it navigate me from point to point to point, and I can do it in different methods. So we can determine like the shortest point path between locations. Now, when we talk about shortest path, that doesn't always mean shortest distance, okay? Because we have transaction costs that might overweigh others, okay? So we'll talk about that here in a minute. So once you have this pieces of information, you can use that vehicle navigation system with your address destinations. You can key that information in, and it can calculate that for you. So you match the address, and then your GPS will determine your current location, and then you're going to get a provided direction for your destination or destinations, depending on how that works. All right, so what do we mean by shortest path and that kind of stuff? So let's talk about this here in a minute. So when you're traveling, let's say, to or from work, you probably have one way that you go most of the time. But of course, you know, if you have a traffic jam in one location, you probably have another couple of alternate routes that you can do. So basically, this is dealing with a travel network, okay? So taking that shortest path, as we said, may mean different things, just depending on what you're dealing with. So the shortest path might correspond to the lowest cumulative transit cost, okay, so between stop and a network. So when we talk about transit costs, these are the things that we talk about, like distance versus time versus velocity versus whatever. So you can have a lot of different things, but you can have a cumulative kind of thing that gives you the scores based on that. So when considering shortest path, you might consider the shortest physical distance, which is what a lot of times people do. But I know shortest path for me, going to work at some times of the day, means something different than shortest path in terms of time. So highway versus city driving. So for instance, if I go early in the morning, city driving is probably my shortest path. But if I go in the rush hour, either in the morning or evening, then highway is going to typically be better for me because the city is pretty congested. So it can maybe take me 30 minutes or less city driving on ideal conditions, where it might take 45 at other times of day. So here's one thing, not making left turns. This has been proven to be really an accident problem, particularly for delivery people. So sometimes some deliveries and whatnot, they don't like these guys doing left turns, so they can program to everything's going to be a right turn kind of thing. So from that standpoint, I mean, it might give you more physical distance by doing right turns, but the potential to have less of a problem in terms of accidents, maybe that can overweigh that. Minimum traffic lights, that's kind of a cool thing. So if you're looking again for transaction costs, traffic lights can be time, and especially in high volume situations, you might have to sit through a light 2 or 3 times before you get through it. Okay, so with a GIS, your segments can be assigned an impedance or transit cost. So when I'm talking about impedance, we're talking about a way of slowing something down, or it's giving me drag. So if I've got a high impedance, it's got high drag, and that's a high transit cost. And what we're trying to do is get rid of that. So transit cost is just the value that represents how many units of time or distance or whatever you're using it takes to move across a network or an edge or a link. And then the accumulation of those, when you add those all together, is what your total values are going to be. So your actual distance is measured from junction to junction, driving time from junction to junction. So a lot of times GIS will know, for instance, length, that's always part of the attribute, but it also might tell you if you're on a state highway, what your maximum velocity is from that junction to that junction. It might be 55, and then it might jump down to 45, and then 35 as you're getting into town. So all that information is held in there. Let's see, I think I skipped something. No, I guess I'm good. Oop, yes, I did skip something. Okay. All right, so shortest path is calculated using an algorithm to determine your overall lowest transit cost. So an algorithm is basically just a program, set of instructions that it uses to calculate it. There's several different algorithms that exist or employed to determine shortest path. The Dijkstra's single source shortest path method is one option. There's what they call the Bellman-Ford single source shortest path option. Floyd-Warshall all pair shortest path. So these are all mathematical models that have been developed over time. Johnson's all pair shortest path methods. I think your author pretty much focuses in on this one, this top one. I'm not even sure if he mentions those other ones. I got those from other sources. So again, those are all just different algorithms that have been developed to allow you to model different things. So what you're doing is you're applying a model to all this information, keying the information, and then it basically just spits out your answer. So what the shortest path algorithm will do is compute your path of lowest cost to travel from source point to each of several destination points or a single within a network. And again, it depends on what you're calling your criteria. Is distance the criteria? Is time the criteria? Is no left turns the criteria? Or is it a combination of those? So you key all that into the algorithm, basically let it run, and it'll find that information. Okay. Constraints on the network are modeled, and they're considered in the calculation. And those are the things like I was just talking about, like traffic lights. Those are constraints. Velocity, those are constraints. Those are the kinds of information in the network. Transit cost, directionality. Are you dealing with ever two-way hitting one-way streets, those kind of things. Okay, so here's an example where you have keyed in the address of, let's say, A, and it's taking you to an address location at B. And what this is calculated is a route for you. And of course, if this was tied to a real-time GPS unit in your car, then, you know, it can navigate you there directly. So sometimes you may want to calculate, sometimes you may want to calculate more than one destination, so we can combine these into one trip. So you may have a need to do a shortest path visit to 3 different locations. So for instance, a shoe store, music store, and a bookstore. Now there's going to be several different ways we can choose to do this. One would be to tell it, I want to go from the shoe store to the music store to the bookstore and back home. Or you tell me what is the best, put it in what order works the best. Okay, so it might take you from the bookstore to the shoe store, then from the shoe store back to the music store, then home, as opposed to me saying I want to go shoe store, music store, bookstore. So it just depends on what criteria you place in it. So there's those 2 possible scenarios. Finding the shortest path when you're using a predefined order, okay? So shoe store, music store to bookstore, that's the way you need to go. Find that shortest path based on that, or find the shortest path when the software can arrange the order for you, and basically it can do it in whatever order works the best to give you the shortest path. So it might come up and it might say shoe store to bookstore first, and then from bookstore to music store. Okay, so it might do that based on those criteria. Okay, so the geospatial application allows you to probably do both scenarios, predefined order or the rearranged order of stops, depending on whether you're letting it happen, or might do both. And then you can also put constraints into that model as well. As we said, things like starting and ending points could be constraints, different starting and ending points. Okay, so you can get, and then you, like I said, you could put other things in there like you want no left turns, those kind of stops, those kind of things. So what we're looking at here, I think you're starting at this one, and then you're saying, I want to go from 1 to 2, and then 2 to 3, 3 to 4, and 4 to 5. So you're doing your own prearranged stops, and you want to do them in that order. Or you can let the software just rip, and you can say, okay, this is just it's doing its own order, and it's finding the best scenario likely, okay? Probably giving you both options, both choices, or you can run each one separately. Okay. So let's take a look at how networks are using geospatial technology. And like I said, we're pretty much all familiar with that. So through your GIS, your network can be created and utilized in a lot of different ways. Of course, we talked about the vehicle navigation system. So these are going to integrate your network concepts, such as you're pinpointing a device's location on a map with GPS. Okay, that's one thing. We talked about the concept of geocoding an address and calculating shortest path. So these are your big things with network technology. So additional options could include concepts of using real-time data to determine location. So things like congestion in an area or high traffic or construction or road accidents. So you have to have real-time feeds that can come into this. And there's a lot of softwares that we have out there. Some of you guys probably have this right now. I forget the name, and there's a couple of them that are used, but they actually have people that, report into this, and then that stuff gets brought into you so that it can constantly recalculate things. It can monitor congestion and monitor high traffic and construction. You can also have some of the DOTs actually can transmit this data, and then that information then can be utilized in conjunction with your navigation systems. So with the real-time feeds, then we can really find out what's going on, and that's pretty cool when you have these kind of things that happen. Anybody got one of those systems that you use that does that?
Now, I use Waze.
That's the one I'm thinking about, Kim. I know, and that one is the one. I think that's kind of a crowdsourced kind of thing, isn't it? The people.
Yes,
that,
it is. You can
yeah.
you can report.
So what's happening? People are constantly reporting that in real time. It's pretty cool because I mean, it'll say you got a car stalled on the right side of the road, like 2 miles up the road, and it's right there when you get there. Yeah. So that one's the one I'm familiar. I couldn't remember the name, but yeah, that's a good one. And of course, it uses real-time feeds, and then you can also do the shortest path based on the considerations above. Okay, so technology has certainly been integrated with smartphones. You've got a GPS chip in there. You've got the geocoding ability, shortest path calculations, and real-time route information, all in the palm of your hand. Everybody's pretty used to that. So similar technology are used on your online services, MapQuest, Bing, Yahoo, Google, Esri Online Maps. Google Map has a street view, which is kind of cool. Gives you that 360 imagery. I think they quit doing that recently. They don't do that as much as they used to. But that was also cool. And you had the cars that were equipped with the special 360-degree views. I'm sure some of you have been driving down the street and see those guys. I used to see them all the time. But this is an example of that. And then that's kind of the unit that they would use to do a 360 capture. Okay, some of these network technologies are also created by companies that specialize in this. Novatech is one that does a lot of the base mapping, and then they sell that to other agencies. So probably a lot of maps that you use are probably produced by Novatech. This Dillamore, I think they're actually someone else now. They were bought out, I believe, but they used to be a big company that produced and sold base maps. They also produce those gazetteer outlets, and they used to be located up in Maine. I've been to their corporate office. It's a pretty cool place, but like I said, I think they got bought out. I'm not even sure if they're in existence anymore. Okay, so that's chapter 8. Anybody have any questions before we move on to that? That's all pretty straightforward stuff, I think. Any questions?
Nope.
Okay, so I want to take a look at some raster issues. So let me do a couple things here. One, under your Blackboard site, okay, there's under weeks. You haven't had a chance to look at this. There is, I believe under chapter 8, what I had in there was this raster info GIS stuff. So we're going to take a look at that. And I also, if you don't have this available, I gave this to you guys the other day. Let me go ahead and make that available real quick. So if you have those, you might want to pull those out. I need to change the date on that, but let me make this active. Let's see. Yeah, I'm gonna make that available. So I gave this out to you guys last week. If you don't have it, we'll take a look at it here. You can download it. So if you have this raster GIS PDF, go ahead and open that up. We're going to talk about a few concepts. Raster does things quite a bit differently than vector. So we're all pretty much vector people. We're all used to probably using mostly softwares that are similar to AutoCAD, those kind of things. So what we'll see is that raster has some other capabilities. So I want to talk about what we call operations on layers. And then we're going to take a look at filtering. So we're going to take a look at local operations. We're going to take a look at what we call local neighborhoods, extended neighborhoods, zones, and those are going to be the kind of primary things we want to look at. So I want to define a few things. First of all, is a local neighborhood is, or local operation is something where on a raster, you are producing a new raster from one or more input layers. Okay, so if we go, let me go over here a minute. So here's what we're saying is if you have a raster, let's see, let me just draw a real quick. So you've got a raster here, and that raster is full of, let's say, little cells that are coded for, let's say, elevation. And that elevation is in feet. And you want to convert that to an output raster that is in meters. So this would be your input raster here. So you got your input, and let's say that's representing feet, and you want an output layer in meters. What you would do is basically take each cell and multiply it by a value that would convert it from feet to meters. So what you're doing is just doing a multiplication in each cell of what the conversion factor is from feet to meters, and you're going to get an output raster. Okay. So what we're talking about here, we're talking about this kind of concept, what we call a local operation. So notice a local operation is going to produce a new layer from one or more input layers, okay? And so you have the value of each new pixel is going to be defined based on the value of the original pixel, and you're going to use some kind of operation on it. So one process is what they call recoding. Recoding is the process of taking typically one input layer, and you're going to assign a new value based on some kind of input. So in the case that I just showed you, it was a multiplication. So you might multiply to get your values, or you might want a range of pixels. So for instance, let's say you've got an elevation raster, and that elevation raster goes, let's say, from 0 to, well, let's say from 10 feet to 500 feet. You might want to range that out. So from 5 feet to 100 feet is range 1. From 500 feet to, or from 100 feet to 200 feet is range 2. So what you could do is have it aggregate all those pixels, and it would range it for you. This is an example of recode, where you can sort your input layers by rank, or you can do a mathematical operation, which is what I was just showing you with the combination of converting from one to the other. So this is typically referred to as a recode or a reclass. Okay, recode or reclass. You guys get the idea on this? Again, just think that what we were just talking about here, you have a elevation of a certain value in feet, and you want to output that as a certain value in meters. So you have a multiplication. What's the conversion factor from feet to meters? So we got 10 feet, right? Here, and we want that in meters. So what's the conversion factor? Nobody knows how many feet in a meter?
Three 3.17 or something?
Yeah, 3.28 typically. I mean, that's
Okay.
close enough, right? So there's 3.28 feet per meter, is that correct? So 1 meter is 3.28 feet, am I right?
Yep.
Okay, so what I'm saying is I would do with this is what? Actually divide. I would divide all the pixels by 3.28, and the new value would be placed in here, okay? And a raster would do this very rapidly. So this is an example of what we would call recode, okay, or reclass. You guys get the idea? Okay, guess I'll take that as a yes. Okay. So the other thing that is a local operation is what's called an overlay. So what you're doing here is you've got your output layer, it's going to depend on 2 or sometimes more layers that are going to be combined together. So what we're saying on this system is this. Let me clean this up. With an overlay, what you're going to have is 2 input layers. There's an input layer A, and here's an input layer B. And you're literally just going to overlay those on top of each other and then do some kind of operation between them. Now, we've already kind of done this in the other chapter, but if this was a raster A and this was raster B, you overlay them in such a way that you get an output layer, okay? So you could add A to B, or you could multiply A to B, those kind of things, but the position of the pixel here is the same position here. So if I take that one and multiply it by that one, the answer goes in here. This is an example of an overlay. And this is an example of what we call a local kind of operation. Okay, so output could be the arithmetic mean. So you could take the average, you could take the pixel position at A plus the pixel position at B divided by 2. Greatest of the 2 input layers, so it would say which one's greater, A or B, and that puts that in there. Or what you can use is this concept of what we call Booleans. So here's an example of this. So this is using a cell, what we call a OR operation. So we notice that in this example, you have cells that are A, B, C. So that could represent soils A, soils B, soils C, and then we have, let's say, elevations. So this could be meters or whatever. So this cell is 6, 7, whatever. So for some reason, we want to know cells that either have A's or 7s. So if it has an A or a 7, that's going to be a true response. So one way to do this is to convert these guys to Booleans, okay, and then do a multiplication or an addition, depending on what you're looking at. So if it's an A, it's what we're looking for, and if it's a 7, it's what we're looking for. So notice what we're doing is we're reclassifying or recoding this. So we're saying anything that is an A is now true, it's 1, and anything that is a B is not true, so it goes to a 0. So this image is just coming from this image. So that's a local operation. Same thing here. 7s are what we're after, so those are true. So those are going to code as a 1. And then that's a 0. And then literally you're just going to overlay this on top of this. So if you say A or B, or A rather, or 7, you can take either or. So when I take and add this to this, I get a 1. When I add 1 to 1, I get a 2. Does everybody see what's going on there? So you come up with a range of 1s and 2s. Anything that's a definite 0 is not what you're after. Okay, that's not your answer. But where both either an A or a 7 exists, it's either a 1 or a 2, and you could further reclassify that. So you could say if it's a 1, it equals 1. If it's a 2, it equals 1. And what this does is this gives you your solution right here. And that showing you anything that has a 1 in it is where either a 7 or an A exists. Now let's look at the logical and. So I have to have both a 7 and an A to exist. So again, we can do the same thing. We can take it because we're looking for A's, those go to 1s. We're looking for 7s, those go to 1s. But in this case, we're going to multiply. So if we take that pixel times that pixel, 0 times 1 gives me 0. 1 times 1 gives me 1. 0 times 1 gives me 0. So ultimately, notice your answer is completely different. So this is saying this is where both the A value and the 7 value occurred. And this was the answer where you had either A or 7. So it depends on what you're doing. It's very, very important to understand the and versus the or. But these are examples of that process of what we're calling local operations. So an overlay in raster is a local operation, a recode or a reclass is a local operation, okay? So now we're going to look at this process of what we call local neighborhoods. So let me draw this, go to this picture here. So a local neighborhood kind of works like this. Give me a sec. When you're dealing with a local neighborhood, what you're saying is I've got pixels out there that surround my target pixel. So I've got a pixel here. I got a pixel here. I got a pixel here. I've got a pixel here, and I've got a pixel here. So these guys immediately connected to it are influencing what's going on here. So this is called your local neighborhood. Notice we have 1, 2, 3, 4. So this is referred to as a 4 connected neighborhood. So you actually also have other pixels that would touch this at the corner. You have a pixel here, you have a pixel here, you have a pixel here, and you have a pixel here. So if you allow this connectivity, what you can have is, this would be 1, 2, 3, 4. In this type of neighborhood, we're calling this, we're excluding these because they only touch at the corners. So this is called a 4 connected neighborhood. If you allow 8 connectivity, then you're saying, I'm going to allow these to influence me as well. Okay. So there's a difference in either what they call diagonal connections, or diagonal and are just up and down, left, right, and diagonal. That's an 8 connected. So this is what we call the 8 connected neighborhood, and this is what we call the 4 connected neighborhood. And depending on what you're doing, you can get some really, really different results. Okay, so let's go over to here and look at this. So local neighborhood is the 4 or 8 immediately adjacent pixels. When you go to extended neighborhoods go beyond that. So we're not going to deal with that too much. So let's come to here. So on the local neighborhoods, the one thing we've got there is this process called filtering. So what filtering is a way of smoothing data or altering data based on applying a filter across your pixels. So you might think of it this way, you know, when you guys download data, let's say if you're out in the field and you shot a bunch of shots, you occasionally get a blown shot. Somebody booted the rod for one shot and then they forgot to change that back in the data collector. So you got some blown shots based on that rod being wrong. So you have to go through and you have to clip those out. So if you have a way of filtering it, you can say, well, anything above this certain elevation or below this certain elevation, I can clip it out. I can get rid of it. That's a filter. Well, with raster, it's a little different. You use this process called a roving filter, and it's a window. These are multiplication values that you place on top of your original data, and what those are going to do is filter out your target pixel. So notice this is called the kernel of your filter, and this is going to do what's called severely smooth it because it's just averaging it. So what it's doing is it's looking at your 8 guys that surround it plus the original pixel. So you put this on top of the filter, or on top of the raster that you're filtering, and you multiply this number times the pixel behind it, that number times the pixel behind it. So these are multipliers on each little pixel value, and then the products of all of these, you just add them together, and that value that you add together goes in the pixel position of where you were. So it's a little confusing, but we'll try. Hopefully I can get this through. One of the things that you deal with here is these should always add up to 1. So if you add this together, you'll see that goes to 1. This one, notice the weight of your neighbors is 0.05 as compared to the center is 0.6. So again, these are big multipliers. You lay this right on top of the pixel that you're trying to filter. So you've got 0.05, 0.05, 0.05. So you're multiplying, multiplying, multiplying. You're going to do that for all of them. And then those products you're going to sum, and you're going to add that together, and that's going to be the target pixel value. So it's considering the pixels that surround it, but the only thing you're actually filtering is the one in the center. And notice this one actually has negative weight on the outside and ultimate weight, higher weight on the inside. So all of these are generating something for some reason. Like for instance, you're trying to smooth out data, or you're trying to enhance data. So it's kind of a way of doing it. So this is I don't know if any of you guys have ever used Photoshop, or if you've used any kind of photo editing kind of tools. This is what these guys actually do, because most of that images are raster, and they're using these filters that they're running across the image. So this is an example of a scanned in version of Mona Lisa. It's not great, but you can see this was the original picture, and running a smoothing filter across it, notice by doing that, you've lost some of the detail. So if you look at the top, particularly like the eyes and the mouth, you'll notice that some of that detail has been blended out because it's been smoothed. And if you look at this bottom one here, let's see, that one's been really severely edge enhanced. So these are the kind of things that filters are doing. And this would be on images, but you can do this with literally any data. And of course, I would have to say, if you're using a filter, you got to know why you're using a filter. But I just want to show you the process. So here's an example. Now, just keep in mind, if you were doing this, you would be doing this for a lot of different data. So this represents a really small little raster, okay? And notice the raster has values of 1, 2, 3 across the top, and then 3, 7, 3, and 2, 1, 2. So those are your raster values. So if we paste this high pass or low pass filter on top of this, we're filtering this guy, that number 7, which is the highlighted one. So to get that number 2.64 there, you're taking 1 times 0.11, 2 times 0.11, 3 times 0.1. You're doing that all around, and then you're taking the last one, ultimately 7.11. Those products, when you add them together, you're saying that that position that was number 7 is actually now 2.60 or 2.64. If we used a different kind of filter, if this filter was filtered for that square, again, you're multiplying 0.05 for the outsides, and then you're multiplying 0.6 for that one, the target. You're adding those together, and you get a value of 0.505. So it's severely smoothed here because we've gone from 7 to 2.64. It's moderately smoothed here, so just dropping it a little bit. But this high pass filter, what that's doing is notice it's completely exaggerated it. So you're multiplying each one of these, 0.1, 0.1, 0.1, 0.1, those are all negative values, and you add that together, the 1.8, and when you add those together, you get an 11. Now, here's the thing to consider when you do these, and this is important, so I'll try to explain this. The filter actually starts at 1, and it'll calculate that position, and then it puts the value there, and then it goes to 2, and it puts the value here, and then it goes to 3, and it puts the value. So you're going to do the whole image based on that. The other thing is, if your target pixel is 1, when you place this guy out here, outside of that filter is missing some squares. Let me go over to this picture and show you what I mean. Let me draw some things here a minute. Give me a sec. This is a little bit of it's not a hard concept, but it's just a little bit of a tough concept to kind of explain. But I'm going to have you guys work through a problem, and hopefully I'll be able to get you guys to kind of understand this. Give me a sec to draw this out. Yeah. Okay.
Are you still on?
Yeah. Okay, so give me a sec to draw my raster. So we have raster values here, okay, and we're just looking at a little piece of this. So if you have, let me just put some values in here for hypothetical. So let's say this has a value of 5 and 5 and 6, and then this is 4 and 4 and let's say 5. Might be elevation, whatever. We're just looking at a really simple example, and then 3 and 3 and 6. So if we're starting, we start the filter here, okay, and then we do the next one and the next one and the next one. So this would be our input raster, and we have that filter. The filter starts here, but because of the filter size, what's happening is the filter, I don't know if I can draw this very well. I'm gonna try to get this, so yeah, that's perfect, okay. So this is my filter actually, and notice out here, there's no values that exist here, right? So if we go back to this picture, notice that filter has values out here, but this picture is showing you I don't have any values here. So if you want to get a true representation when it filters this square right here, what you have to do is you have to use some kind of value out here. So what I typically do is I say, because spatial variation tends to be the same left and right, I would call this 5. Whoops. I tend to call this 5, 5, 5, 5, and 4. So what that's going to do is give me a better representation, because if this was 0, 0, 0, 0, 0, that wouldn't filter very well. Okay. So once you do your filter on this square, you get a number here, you put that in the output layer, then this filter, it moves to the next. So this was my target filter originally. Now this is the filter. The filter's moved across. You're going to filter that one, then it comes here and it filters that one. Then it drops down here and it filters and it filters and it filters, and it does this for each location. You gotta envision, if you do these filters, doing them by hand are pretty involved, which I'm gonna have you do a little sample of this just to kind of show you how this works. But if you're doing this in a GIS, it happens pretty rapidly. But this literally is kind of how like photographic filters work when you're dealing with, like, say, Photoshop or something. It uses the same kind of process. And what it's doing is it's using this. This is your local neighborhood. So this is your local neighborhood of values. All right. So that's what we would call a filter. And again, I'm not going into the reasons of why you would use filters. I mean, that's just kind of something that you would also have there. So when you talk about extended neighborhoods go beyond the 8 surrounding. Okay, so things like distance, you can calculate the distance from target cells to each cell or nearest several cells. Buffers are examples of extended neighborhoods. That buffer can go out further than just one single cell. And your buffer, we've talked about buffers enough, but the buffer could result in 3 layers. So you could have a 1 for the original object, 2 for the buffer region, and anything outside of the buffer would be 0. So we've talked about buffers quite a bit. Another thing that we have here is what we would call a view shed. And if you've never heard about view sheds or heard of these before, these are pretty interesting, because this allows you to determine, if you are standing at a certain location, what you can see from that location. So if you have a topography map using the viewshed technology, you can say, I'm standing at a certain location. So if we go back to this example, you're literally saying, I'm standing right here. And it says, okay, what can I see from here based on the other surrounding pixels? So it kind of goes and it looks out and it looks in all directions, and it says whether you can see something from that point or not based on what you're looking at. And of course, if you have hollows or you have something that's obstructing it, it wouldn't allow you to see that. Anybody know who uses that technology a lot? That's a very commonly used technology. Anybody have a guess of somebody who would use that? Nobody? Cell phone sighting when they sight cell towers are very often sighted based on viewshed technology, because they have to put a cell tower at a certain height and at a certain location that gives you the most coverage. And even so, even if you do use that, sometimes you have dead spots. That would be the point that you can't see line of sight, because radio waves basically got to be line of sight. Okay, so viewshed technology is really pretty neat thing. So let's I want to look at one more thing on local neighborhoods, and this is called slope and aspect. So slope is, I think I got my slides a little bit out of order. Probably should have had this one first, but slopes are determining slope between several pixels, and aspect would be the thing that something is locally tilting. And so let's go back to this diagram here. Let me grab this, let me undo some of this. I'll show you how slope and aspect worked in this picture here. Okay, so let me, I'm gonna refill this. All right, so let's say I want to calculate the slope here. So this represents, let's say, I don't know, let's say this represents feet of elevation. So we've got let's say we've got 5 feet, 5 feet, 10 feet. Let's say maybe this is 4 feet. Maybe this is 8 feet, 7 feet, 1 foot, and 3 feet. So what we want to do is come up with an image that's, instead of having elevation, we want to know what's the slope in this in percent grade. Okay. So if this is our target pixel, what we're going to do is they're going to have an output layer that's going to give it in slopes. So first off, what you're going to do is I would have an output layer. So somewhere in here, this is pixel is going to represent that pixel. Okay. So what I first do is I also have to know what the distance is on my grid squares. So let's say this represents elevation. Elevation is in feet. Let's do this. Elevation is in feet. And this grid square is, let's say, 50 feet by 50 feet. So that's not the raster. It's what I'm saying is that represents 50 feet by 50 feet. Okay. So what we're going to do is calculate the slope, and we're going to do it in 8 directions. So first off, I look at which way water would flow. So if this is my target pixel, this is my target pixel. In this case, it's flowing in, it's flowing in, it's flowing in, flowing in, flowing out, flowing out, flowing out, flowing in. The reason I do that is because that establishes what we call the aspect. In other words, which way this thing is locally facing. So what we're going to do then is go through and calculate slope values for each one of these. So if I go from the center of that pixel to the center of that pixel, this distance is 50 feet. So the slope there would be rise, which would be 5 divided by, or 5 minus 4, which would be 1 divided by 50. So that would give me 1 divided by 50. That would give me at 0.0. 1 divided by 50 would give me 0.02 of a foot per foot. But if I put that into a percentage, this would be a 2% grade. 2%, not 20%. Okay. This one would be from 10 to 4 would be 6, but the distance here from center of pixel to center of pixel is not 50 feet. It would be 50 squared plus 50 squared. Square root. So the diagonal distance is going to be 70.71 feet. So this would be 70.71. So the slope on this would be 8%, basically 8.5. So you're going to keep doing this for each location. So this is 2%, that's 8.8%. 8.5, that would be what? 4 divided by 50. I think you're getting, hopefully you're getting the idea. So it's going to compare all of those. This is 8% slope. And so it's going to go through and it's going to compare all of these. You get a 6%. So what it's going to do is it's going to return the highest value, and the highest value happens to be this. So this grid square would now have a value of 8.5 in it. So it's going to do that for each position within this. So you get like 8.5. You get, instead of your image being in elevation, it's going to be in percent slope. Okay. An aspect is referring to the way this guy's locally tilting. So because this is coming in, this is your highest range right here, this is your 8%, then the aspect, this thing would be locally facing or locally tilting in a southwest direction. Because notice this is tilting that. An aspect is important because it has to do with things like the way sun might strike something or the way water would flow. So you could have that pixel called southwest, or you could also have that 8.5 and southwest, or just 8.5. So that's what we're talking about back here when we talk about slopes and aspect. So you're calculating the slope based on the elevations, looking at the differences in the pixels and their neighborhood. Remember, it's always an 8 connected typically. And the steepest slope is the one that you call the value for slope, and then the aspect itself. Aspect is usually measured from north. That's really important. Like I said, aspect is important for analyzing things like vegetation patterns and computing energy balances. Or you look at erosion. You guys can definitely see aspect in the wintertime. If you're in an area where snow, you had a lot of snow cover, and then as the sun starts to get warmer into the February and March, if you got snow standing on the ground, if you go in some southern facing slopes, there may be no snow because it's all melted off. But in the north facing slopes, you still maybe have a lot of snow, and that's a concept of aspect. You can graphically or physically see that. Okay, so, and it also affects things like runoff, and so for drainage patterns, those kind of things. If you've ever done slope arrows in, like, say, Civil 3D, where you're doing, well, those are a little different, but those are really showing you aspect of your triangles. So that's what we're talking about here. And then you have some other things you can calculate, like areas and perimeters. Area is very interesting when you talk about raster, because the size of the grid squares and the orientation of the grid squares with respect to the object, or the object with respect to the grid square alignment, can make a huge difference in terms of how you calculate perimeter and area. Let's look at this picture here. This is a really good picture to explain that concept. Notice each grid square here, as you see that, is 1 unit by 1 unit. And so this is your target thing. It might represent a building, it might represent a parcel of property, whatever. But if this is 1 unit, so we have 1 unit times 1 unit, so that's 1 square inch or 1 square foot or whatever that is. And you're just taking the number of squares that you have and you're multiplying them by the value. So you have 1 square unit times 16 gives you 16 square units of area, and the perimeter is just counting around 1, 2, 3, 4, 5, you just count it around. So you get 16 square units and 16 linear units. So notice, if this actual object that you are portraying in the raster is skewed with respect to the grid, what happens is, notice your grid squares are totally different. So again, you have 1 unit times 1 unit times the number of squares we have in here, and there's 18, so 18 times that gives you 18 square units. Well, if that's square feet or square miles, 16 square miles versus 18 square miles is totally different. There's a lot of difference in the area. Also notice perimeter. Perimeter just adds the sides up, so notice perimeter gets bigger too. So which is correct? Well, it doesn't necessarily, you don't really necessarily know, except that if this completely lines up with the grid squares, raster units, then this is going to be a more correct value. So, but this can make a huge difference. So the orientation with respect to the actual grid itself makes a huge difference when you calculate area and perimeter in raster. Bottom line, in raster is not going to be as accurate for doing things like this or this, because it's limited to how big your grid square is. So if your grid square is 50 meter by 50 meter resolution, that's not going to be as accurate. So if you can go to a smaller grid square, you're going to have a little bit more success, but then it becomes kind of a trade-off in terms of time and calculation power. Okay. So you guys can read through this, and I got a little quiz, or not a quiz. I have a little homework assignment that I want you to do that deals with this. Let's pull that up. I gave this to you guys last week. If you don't have it, this is available now. I'm going to open this up, so we'll take a look at this. So what I have here on this sheet is I have this raster, and this raster A represents feet and elevation. It's what we call a 6x6 raster, so it's telling you got 6 grid squares by 6 grid squares. Each raster is going to be considered, or you're going to consider it an 8 connected. So when you do certain things with it, that's going to be important, 8 connected. So number of zones, let's go back to this. I didn't talk about zones. Let me look at zones real quick. I don't know if I got that on there. I should. Okay, a zone. A zone is pixels that are connected to each other, and that's just a way of isolating it out. So let's go here real quick and look at this. So if we allow on this raster that we're just looking at here, let me see if I can get rid of all of that. Let me erase this. So if we have this raster, and let me just replace it with some simple values. Let's say 1, 1, 2, 1, 2, 2, 2, 2, and 1. Okay. So we could have a zone here that would be the connectivity of ones, right? Right there. But it would depend on whether you allow 4 connected or 8 connected. So if you only allow 4 connected, you're going to have this zone would be portrayed by that data right there. Because say that would be one zone. Okay. This guy would be excluded because he's not connected if you don't allow 4 connectivity. So in this case, you would have one zone here. You would have one zone here. You would have one zone here, and you would have one zone here. Does everybody get the idea on zones? Anybody still there?
Yes.
Yeah, I'm not on the first one where you circled the ones.
Yeah.
Are you using a 2 as
This
the
one here,
zone?
Greg? That one
Yes.
there?
Yep.
Okay. First of all, understand what I said. I'm only allowing 4 connectivity, all right?
Mm-hmm.
So that means these guys can only connect top, bottom, left, right. This is excluded right here, okay? So let me undo this back. All right, so if I say it's 4 connected and I look at this zone right here, this is one zone right here because I'm just looking at the number ones that have the same value, okay? And because they can only connect up, top, bottom, or left, right, this is excluding this number 1 over here.
Okay.
You see that?
Yep.
When I look at the 2s, these guys are connected top, left, right. So that's another zone. So this
Okay.
would be one zone. That would be a second zone.
I was looking at it more of a square and not a numerical.
What you're looking at when you talk about zones, you're combining squares together that have the same value. Okay.
Gotcha.
All right. So this doesn't have any connection. So this is a zone, and it's an isolated zone, and that's an isolated zone. So this image, now think about what I'm saying. This image under a 4 connected neighborhood has 1, 2, 3, 4 zones. Everybody see that?
Yep. I'm with you again.
All right, now watch this. If I go to 8 connected, when I go 8 connected, it allows top, bottom, left, right, and then diagonal connectivity. So this gets connected like this. There's one zone. Do you see that?
Yep.
Now we're looking at that being one's, well, actually, let me do this. This is weird. This is going to connect in like this, like that. So with 8 connectivity, we have only 2 zones.
And they can't, I guess they can overlap.
Yeah, because technically they're overlapping at a point, right?
Okay.
See that? Because they're connecting adjacently, right? So that's kind of weird. You see that? Now
Yeah.
think about this. If you were isolating these and saying this was a building, would it make sense that this is a building? Probably not, right?
Right.
So 8 connectivity may not make sense in that sense, okay? Does that, you guys get the idea now?
Yeah.
It's kind of a weird process, but what I'm saying on my picture, let's go back here now. What I'm telling you here, well, where'd I put that? Let's see. Come on. Just have to fire this up again. Hold on a minute. Ah. What I'm telling you here on this homework is that this is 8 connected, okay? All right, so it asks you to identify the number of zones. Patch is another name for a zone. So let's look at this. If you start here at 97 and it's 8 connected, there's no other 97 connected to this, correct?
Correct. So 97 would be one zone.
Right. Now here's the easiest way to do this, okay? Get yourself some colored pencils, okay? And color that in red. Now, when we look at 96, 96 connects from here to here, and it looks like that's the only connection, right?
Right.
Color that blue. Now when we go to 95, 95 connects to 95, and it connects to 95, and there's another zone, okay? So I want you to determine the number of unique zones that exist here, and you're going to allow 1 pixel to be 1 zone, okay? Has everybody got the idea?
Yes.
So now classes are the number of values that are represented in this raster. So that's very simple. So just look for your lowest value and your highest value, and if there's anything missing in between. So if I'm going, what's the lowest value in this raster? Looks like 91, right?
91.
And we're going to set 97, looks like the high. So as long as we've got 91 to 97, that would be the number of zones we would have, okay? So we got 1, 2, 3, 4, you see the idea? But if you've got 95 missing, then you won't have the same number. So you don't have that issue. So, but you should everybody should easily get the classes. Zones you have to be careful with, okay? Zones you really have to be careful with. So just try this I want you to try this for Thursday. We'll take a look at this on Thursday, okay? All right, so what I want you to do here is take this raster A, which is what we call a digital elevation model. That's what DEM means, and it's in units of feet. So that's basically a DTM. That's a representation of the Earth's ground topography. And I want you to create this output raster here with units in meters. So basically, you're going to convert this from feet to meters, place the meter value in here, feet to meters, you're going to do that for each grid square, okay? Then I want you to tell me, is it a local operation, a local neighborhood, or an extended neighborhood operation? Okay, is everybody okay with that? That's your first page.
Say number 3 again. You're wanting us to do what in meters?
I want you to convert this image from
Okay.
feet to meters.
Okay.
That's all you're doing, okay? So
Yep.
you're basically multiplying each one of these values by the conversion factor from feet to meters, correct?
Yes.
And then that would just be that value would be put down in here, okay? Now, here's the thing. You may have to make a decision because it's not going to be a perfect number. So it's not going to go from an integer to an integer. So you're going to have a real number. So maybe just go to 1 decimal place, round it to 1 decimal place, okay? Because you'll have multiple decimals values. Everybody okay with that?
Yep.
All right, so the second page is probably the hardest thing. It'll take you a while. Oh, geez. I'll tell you what, let's just skip this. I'll go over this with you on, wait, do you guys have a copy of the one I gave you?
Yes.
I think yours is different. Hold on a minute.
Yeah, I'm looking at it.
It's different, doesn't it?
Yes.
It is.
Okay, here's what's different. I gave you the actual kernel, okay? So your kernel is, it says 0.05, 0.05, 0.05. That's your filter, okay? So
Yeah.
you don't have to produce the filter. The filter's already produced, okay? So what you're gonna do is you're gonna start that filter on this cell, and you're gonna filter that cell, and then you're gonna put the information here. Then you're gonna bring the filter over here, and you're gonna put the information here. Then you're going to filter that cell. You're going to do that for each one of these. So you're going to have an input layer of this and a filtered output layer. Okay. That takes you a little bit of time to do. The one thing that I would do that I just showed you is to do this filter properly, put the 1 out here, 3 out here, 5 out here, 7 out here, 7 diagonally, 7 this way. So you get what I'm doing? I'm just ringing those around, okay? Because if you don't have a value out here, what will happen is you'll get really, really skewed results for the edges of your data right here, okay? So if you're having troubles with this, just wait. I can answer those on Thursday. But I think just give it a try, see what you can come up with, and I'll get the new sheet on this because this one I've got on there's an old one. Okay. Any questions on that? This will probably be the hardest thing for you to do. No questions?
I don't think so.
Okay, just try it, and if you have questions, then you can ask. Okay. So the last one's giving you a raster, and I want you to determine the slope and the aspect for 2 cells. You're not doing it for the whole image. You're just doing it for 2. And I think I have another sheet you can use if you want at the back to do this on. So this is a digital elevation model. These are in meters, I suppose. And this is 250 by 250. So you need to figure out what the distance is across here. That's not hard to do, okay? And so if we are going to determine the slope on the aspect for cells 1, 1, and 2, 2, that's column versus row. So notice 1, 1, 1, column 1, row 1 is this cell right here, 730. So you're going to determine what is the slope and what is the aspect here, and you're going to use the 8 connected neighborhood around it to do that. For column 3, row 2, column 3, row 2, you've got this 740 value. You got this 8 connected neighborhood around here. So you got to calculate the slope on each of its neighbors and determine which is the highest value. That would be the value that you're calling it the slope. And then the aspect is the way it's locally facing. So again, try these. If you have any questions, we'll go over this on Thursday, okay? I think you won't have any problems on the first page. First page is probably pretty simple. This stuff is simple. Colored pencils really do help, though, if you're trying to figure out the zones here, okay? I definitely agree. I definitely recommend that. So number of zones, number of classes, and then I want you to recode this or reclass this to meters. And then we're going to do the filter on this using the kernel that I've provided. And you're going to use, this is your input image that you're filtering. This is going to be your output image, okay? That's the hardest thing right there to do. And then we're going to do that slope and aspect for that pixel and that pixel, not for all of them, okay? Try it for Thursday, and I'll answer questions on this first thing. And then we're also going to be doing the lab 8 out of here, which actually I think uses Google Earth on this one. So that'll be a pretty simple lab to get into. Okay, does anybody have any questions then?
Oh, that's it.
Yep, that's it. So raster's a little different, okay, but give it a try because your book, he doesn't go over a bunch of this stuff, and it's actually kind of cool to see how it does that. So, and I can talk a little bit more about this on Thursday just to see, but give it a try, okay? And that's all I'm asking, and then we'll take a look at it. All right. Any questions?
No, sir.
All right.
Not at the
great.
moment.
Okay. Well, if you have some questions, just shoot them to me. I will be around tomorrow. I've got office hours 8 to 10 or 8 to 1. And then I definitely will see you guys then on Thursday, and we'll do that lab, and then we'll look at this stuff first, and then we'll do a lab. Probably have a little quiz over chapter 6 as well, or 7 rather, chapter 7. Okay.
All right.
All right, great. All right, so I'll go ahead and get this. I'll get the stop the lecture, and I'll get this formatted, and then this should be